In this video, I'm going to walk you through the calculation steps required to do the sheet metal bending using one of the questions from your A2-2 assignment. Let's look at question number 1. I've redrawn the picture so it's easier to see. You can see that the one leg has 2.25 in length and then 2.40 in the other length. And it's bent 90 degrees using the radius 1/8, and the material thickness is 40 thou. So what is the first question? What is the minimum bend radius? The minimum bend radius is given to you in a chart, typically using the AC 4313 or your manufacturer's maintenance manual. Or you can use the general rule of thumb, the 3 times the material thickness. In this case, I'll just use the 3 times the material thickness to figure out what my minimum bend radius is. So what minimum bend radius is that the radius that you're trying to use cannot be smaller than the minimum bend radius suggested. So let's look at an example here. So you got a material that's 40 thou, and I'm going to times that by 3, which makes it 120 thou. And I have a radius that's 1/8. 1/8 in decimals is 125 thou. The calculated value was 120, and I have a radius that's 125, which is more than the minimum bend radius, which means I'm good to go and I can use it. The next question is, what is the setback? If you remember from my last video, you can see that the setback has a formula of radius plus the thickness times by the K value, which is our K factor. Do you guys remember what the K factor is? K factor was the ratio between the distance of the neutral axis to the inner side compared to the whole thickness. All right? But how are you going to find that out? It will be very difficult for you to measure that every time, wouldn't it? So the engineers and the scientists have done their research and their experiments and figured out, hey, there is a consistent value to it, therefore we can put that in the chart. So if you flip to the first page of your assignment, A2-2, we've given you the K factor in a chart form. So one side has a degree, one side has the K value. And the reason why I didn't use the K in my setback formula in the beginning from my last video was because if you scroll down to 90 degree, well, the value is 1. However, it will be wrong not to use this K value as part of your setback formula. This is your complete formula and you guys need to memorize this. So, what is setback? Well, setback is the distance between the bend tangent line. Bend tangent line is where the bend happens or ends. All right? So, in this case, your bend tangent line will be over here. It will be the distance between the bend tangent line to the mold point. Right? And that will be our setback. And again, same thing. This is your bend tangent line where the bend ends or starts to the mold point. That is your setback. Every bend will have 2 equal value of the setback. Right. So why was it then a radius plus the thickness? Well, if you look at it, hey, I have the thickness of the material plus the radius, correct? So if you add these up, I'm going to get a setback. Again, for this one, you have the thickness, and you add that with the radius, and that's how I'm going to get a setback, correct? That's why we came up with this. So if I plug in the number, the radius is 125 thou plus the thickness of 40, and times that. What is the K value for 90 degree? It is 1. So I'm going to get 0.165 inch for my setback. So I can put that down That is your setback. Right. What is the next question? The next question is, what is the length of each flat? What is the definition of flat? It is the material that is not used in a bend. In this case, I've already shaded them in black. I got the flat 1 and flat 2, as the name suggests, flat surface, meaning they're the material that is not being used in a bend. So how do you calculate that? Well, we have the total distance on one side, and we also know what our setback is. Setback suggests the distance between where the bend happens or ends to the null point, where it happens to be the exact same point here. So if I was to subtract the setback from the total distance, wouldn't I be getting the flat 1? Absolutely. And that goes same for flat 2 as well. Right? So let's do the calculation. We got 2.4 as your total distance on one side, minus your setback, which is 165 now, and that's going to give me, fortunately, I don't have a calculator because I'm using it to record it, but it's going to give me 2.235 inches. That is the length of one of my flat. What about flat 2? It's exactly the same procedure, 2.25 minus 1 of the setback. That's going to give me 2.085 in it. Right? We have two flats, 2.085, 2.235. Now, what is the bend allowance is the next question. What is the bend allowance? Well, it's opposite from flat. Bend allowance is the material that's used in a bend. Well, how do we know that? Again, it's given you in a chart because the scientists and the engineer did a whole bunch of experiments using the same material thickness in the same degree of bend, using the same radius. They were experimenting, why am I gonna get the same amount of material that's gonna be used in that bend? And the answer was yes, they were getting the consistent result. As long as their material and the degree of bend in the same radius was same every time, well, they were getting the exact same results of material that's used in that bend. So that chart is in the handout that I've given you, the paper format. So you can use it. I'm going to the chart, paper printout, and I'm getting for my 40 thou, for the 90-degree bend on the radius 1/8, I'm getting a 224 thou, which means in this area, right, when my material is 40 thou, 90-degree bend, this area is going to be 224 thou. Every time, doesn't matter how many material of 40 thou you're bending at 90 degrees. It stays consistent. If you look at the chart, you're going to see another number underneath. And I can explain what that number is in the next video, right? Anyways, that's bend allowance. The next is total developed length. Now, these two are the new ones that I'm introducing in this lecture, in this video, right? The total developed length is the total length that I require to do this fabrication. If I was to tell you, if I'm to give you this schematic and then, hey, go build this, how would you know how long of a piece that you have to cut? Well, it would be easy if it was a paper, wouldn't it? Right? If it was just a paper at 90-degree bend, then simply it will look like this. One side being 2.25, right? And then one side being 2.4. The total distance, length I need for this paper will be 2.4 plus 2.25, which is going to be 4.65 inch. As long as I cut my paper into 4.65 inch long, I can do this. However, is it going to be the same for this guy? Maybe, maybe not, but most likely not, because I have this radius bend, correct? So that's what it's asking. Let's just look at it now. All right, let's pretend if I was to grab this bent piece I'm gonna Hulk strength, and I'm gonna open it and make it flat again. I'm cheating. Instead of calculating all that, I'm cheating. I'm trying to like open that up and measure that length, right? It's not gonna really work because if you cold work it, it's gonna break, it's gonna wrinkle, it's not gonna work. But let's say in a perfect world, I was able to do that. I open that up to measure it. Well, what would it be? What would it look like? Well, it's gonna look like this. I open it up, and I have one side of the flat, and then the other side of the flat. And in the middle, what would I have? Yes, I will have my bend allowance. Correct? If I was to open this up, it will look like this. And my TDL, total developed length, would be the sum of flat number 1 plus the bend allowance and the flat number 2. The sum of these 3 dimensions is going to give me the total length, the total developed length of this sheet to fabricate this. So let's go ahead. My TDL is going to be 2.235 plus 224 now plus 2.085. That's going to give me 2.459 plus 2.085 and 4.544. That is going to be the total length. Now let's compare that with my paper. Is it going to be longer or shorter? By the look of it, hey, my sheet metal needs actually a shorter length to achieve the same length on both sides. 2.25, 2.25, 2.4, 2.4. The paper needs a longer distance than this guy. Why is that? Well, that's because, if you guys remember, where the bend happened, one side compresses and the other side stretches. You're stretching the metal, therefore this becomes thinner, right? Therefore, you don't need this full length to achieve this. All right? Because there is a little bit of stretch in the metal. You actually need less of it, which is a good thing for us, right? All right. The last one is the sight line. Thing that we need to know for this. The question is, okay, I figured out now the total length, how much I have to cut and all that. But the question is, hey, how much do I have to put in the brake, the material, let's say, to achieve this 2.25 on one side and 2.4 on the other side? How would you figure that? So, I'm going to draw again. There's more of a sharp bend this time. Shouldn't happen. That's my radius, my ball. So we don't know how much I need to put it in to achieve that exact distance, correct? I'm going to extend this like so. What does that look like? Well, this is the lip of the brake, and this, the ball, was the nose part of the brake. The ball that I drew there was the nose portion of the brake the whole time. This is what it looks like, right? So we need to figure out about when is it going to bend. Well, as you can see in this picture, that everything rides upon the tangent line of this radius, the ball, right? Correct? Which means, hey, if I was to draw a straight line here, this is where the bend is, where the material is getting wrapped around. So let's pretend this bend didn't happen, and I am putting in my flat piece in there. This is this piece, looking at it from the side, right? I'm putting it in to do the bend, maybe a little thick. Right, maybe As you can see, I was doing the bend according to the end, the tangent line of this radius, correct? Everything was just kind of wrapped around, right? So, where does the bend start to happen? We know that the bend tangent line either starts or ends the bend, right? That happens right there, which happens to be at the radius point, right? That is your bend tangent line. This is your flat. If that's the case, correct? That is your flat 2. So I just need to figure out this distance, right? I just need to figure out, what is that distance? What does that look like to you? Oh, it's the radius again. It's the radius again, right? So this is the last formula of this calculation. The sight line is equal to flat plus the radius, right? So the way that you measure this sight line is going to be from that edge that you're putting it in, and then you're going to mark it, right? And that line has to line up exactly to the tangent portion of this brick. Those are the brick, and you should be looking at it. This is my eye, directly from above, 90 degrees down. All right? To line this up, on this sight line, okay? So let's finish this. My flat is going to be 2.085 plus the radius 125. We're abusing this radius, right? And that becomes 2.21. 2.21 inches away, well, from the edge of the flat 2, right, is going to be my sight line. Remember, when you're indicating your sight line, you also want to indicate which direction you want to put your sheet into, because if you draw the sight line from this edge to here, but if you put the flat 1 in there, you're going to get a completely different bend. You're going to get a complete different result, and you don't want to do that, right? So make sure you indicate in your sheet which direction you're going to feed your piece into the break. Does that make sense? Perfect. Cool. Well, that sums up the calculation portion of the sheet metal bend. And there are 5 more questions like this, a bit more complicated, but I'm sure you guys will be able to figure out. If you got any questions, feel free to ask me, and thank you very much.